Hi everybody, welcome back. I'm Amy Jensen, and today we are going to talk about graphing advanced rational functions, as well as identifying some of the characteristics of the graph and how to find those characteristics. So grab a pencil and some paper and let's get started. First, let's review what is a rational function. Well, recall that a rational function is when you have a polynomial divided by another polynomial. And in this case, g of x, the denominator, cannot equal 0. Some of the other characteristics you'll be asked to find are the x and y intercepts. Remember, we want to give those as a coordinate point. The vertical asymptote, which will be x equals something. The horizontal asymptote, which is y equals something, as well as sometimes we have a slant asymptote, which is in the equation of a line. And of course, we're usually asked to state the domain. And of course, the domain are the possible x values. So I'm going to take a few minutes and just review how to find each of these characteristics, as well as what the correct notation is for writing your answer. And if you don't need this, then just skip ahead and we'll do 3 problems worked out completely after this. So x-intercepts, first of all, we need to just set the numerator equal to 0 and solve for x. And we want to write that as a coordinate point. Remember, it will always be whatever my x value is, comma 0. A y-intercept will only have one y-intercept. And for a y-intercept, we just need to plug in x equals 0 into the function and solve for y. And we'll do examples of all of these. Okay, so let's talk about how to find the asymptotes of a rational function. The vertical asymptote, we just want to set the denominator equal to 0 and solve for x. And this will give us the values of x that would make the denominator equal 0, and therefore the function is undefined. So recall that the function will never cross a vertical asymptote. They're barriers that are set in stone. We can't break those rules. For the horizontal asymptote, it depends. So we really need to look at the highest degree of the polynomial in the numerator and compare that to the highest degree of the polynomial in the denominator. In other words, we're just looking at the exponent in the top and the bottom. If the bottom exponent is bigger than the top, like we have this one here, 3 is bigger than 2, in this case, y equals 0. That's my horizontal asymptote. If the top and the bottom are equal, the exponents are equal, then what we do is we calculate the ratio of coefficients for the leading x term in each polynomial. We just find the fraction in front of the x squareds in this case. So we just look at the coefficients, and so we get 3 over 5. And then lastly, the third situation, of course, is if the top is bigger than the bottom. So for example, x to the 4th divided by x cubed, 4 is bigger than 3. And in this case, we don't have horizontal asymptotes, so we just write none. So unlike vertical asymptotes, horizontal asymptotes are really guidelines, and sometimes a function will cross the horizontal asymptote, especially when it's close to the origin and closer into the x and y axis. The horizontal asymptotes are really giving us the end behavior tendencies of our function on the graph. So when we don't have a horizontal asymptote, then we need to check for a slant asymptote. A slant asymptote is just the equation of a line. So you take the top polynomial and divide it by the bottom using either long or synthetic division, and we just ignore the remainder. And what we get for the equation of the line is the result of our division are the coefficients of the the equation of our slant asymptote. We'll do some of those as examples in just a minute. And then lastly, we get holes or points where the function is not defined when we have common factors in the numerator and the denominator. So when you simplify a rational function and you cross out the factors, you need to identify that there is a hole at that point where you crossed out that factor. So the function is still undefined at that x value. And then to find the y value, you simply plug in your x into your simplified function to find what the y would be. Write that hole as a coordinate point. We'll do an example of this as well. So let's try 3 different examples. And if you feel pretty good about this, pause the video and try these on your own. Then use the video to check your answer. And if you don't feel good about this, then just work these problems along with the video. So here we go. Example 1. We have our function, f of x is equal to x squared plus 3x plus 2 all over x minus 2. We're asked to graph the function and then find these characteristics. The first thing we always want to do is factor. So let's factor the top, the bottom. There's not much we can do there. And then that will help us identify if we have any holes. If our factors crossed out and simplified, we might have a hole. Then we can go on to find the x-intercept. So recall with the x-intercept, we need to find where the numerator is equal to 0. So to do that, we just simply set our factors in the numerator equal to 0 and solve for x. So we get x equals -2 and x equals -1. And recall, you want to write your x-intercept as a coordinate point. Now, if it asked you just for the 0, instead of the x-intercept, you would write just the x value. But in this case, we're asked for the x-intercept. Okay, y-intercept, that's one of the easiest things. Just plug in 0 into your function. And in this case, you might want to plug it into the original function. So you would have 0 squared plus 3 times 0 plus 2 divided by 0 minus 2. So basically just cover up anything with an x and it will simplify to 2 divided by -2, which of course is -1. So the y-intercept, again, we want to write that as a coordinate point. So this will be -1 for our y value. So we write that as 0, -1. Okay, next, the vertical asymptote is simply where the denominator equals 0. And we write this as an equation. So solve for x, we get x equals 2. So the function is not defined where x equals 2. So write your vertical asymptote as x equals 2, not 2. Make sure you put x equals 2 as an equation. All right, horizontal asymptote. Remember, we have to look at the exponent in the numerator versus the denominator. The top exponent is 2, the bottom exponent is 1, so 2 is bigger than 1, so we have no horizontal asymptote, which means we need to look for a slant asymptote. And remember that you can use synthetic or long division to divide the numerator by the denominator. So x goes into x squared x times. So we should have x times x is x squared. X times -2 is -2x. So remember, we're subtracting that, and so we end up with 5x. So x goes into 5x 5 times. Multiply the 5 times the x and the -2, and subtract. And we're left with a remainder of 12, but remember, we don't care about that remainder. We just care about the x plus 5. So ignore that remainder, and that x plus 5, that is the equation of our line that is our slant asymptote. So write that as an equation, y equals x plus 5. Really important that you write the asymptotes as an equation, which means it has to have an equal sign. So now let's talk about the domain. So the function is not defined when x equals 2. So I can use my vertical asymptote here, and I'm reading my graph left to right when I'm trying to identify the domain. So I'm going to say from negative infinity until I get to x equals 2, and then from 2 to infinity. So let's graph this. First, let's start by putting in the vertical asymptote at x equals 2, and we'll show that as a red dotted line here. Yours doesn't have to be red, but mine is red here. And then we'll do the slant asymptote. So start at the y-intercept at 5, and then we have a slope of 1. So we just want to show a hashed line there for the asymptote. And then you probably need to show your x-intercepts and your y-intercept. So we're going to show those as distinct points. So -2, 0, and -1, 0. Those are the x-intercepts. And then 0, -1 is the y-intercept. So when I draw my graph, I need to make sure to go through those points. And remember, the graph will always hug the asymptote. So I really don't need any other specific points other than to go up through the x-intercepts, make sure you go through the y-intercept, and then hug the slant and vertical asymptote. So the other part of the graph to the right side of the x equals 2 vertical asymptote, we need to just pick any point on the right side of x equals 2. So let's try x equals 4. If I plug in x equals 4 into the function, I get y equals 15, which just tells me that the graph is going to be somewhere up here. And again, I'm not going to be exact because it's such a big number, it kind of goes off my graph. So I just want to show that the graph is in this little area. And again, it'll go close to both the vertical and the slant asymptote. So we're just trying to sketch the graph here. So as long as you show your distinct points of your x-intercept and y-intercept, and then sketch your graph hugging those asymptotes, you should be fine. So all of these rational functions are slightly different, but with enough practice, you'll get to see a little bit of each type. So again, first thing we want to do with our second example here is factor. So we always want to factor first. So in this case, again, we don't have any holes in the function because we don't have any factors that are crossing out on the top and the bottom. We do have x-intercepts, so setting the numerator equal to 0, that's pretty easy. We just get x equals 0, so 0, 0. Our y-intercept, plug in 0 for x, and we get 0 in the numerator, so we get 0. Okay, so the vertical asymptote, in this case, we're going to have two vertical asymptotes at x equals -2 and x equals 2. Remember to write those as equations, not just the number. And then the horizontal asymptote. So in this case, the number is bigger on the bottom, the exponent, so we get a horizontal asymptote of y equals 0, which means we don't have a slant asymptote. So now domain, let's look at the vertical asymptote and write our domain. So basically the domain, if we're reading from left to right, it's going to jump over the values in the vertical asymptote for x where the function is undefined. So let's sketch out this graph. And sometimes people like to write the domain after they graph. That's totally fine, whatever floats your boat. So we have three different asymptotes here. One horizontal asymptote at y equals 0, and then our two vertical asymptotes. So for this graph, I would, again, make sure you show the x-intercept and y-intercept, which are the same point right there at the origin. And in this case, this is going to be one of those examples where our graph could cross the horizontal asymptote close to the origin. So what I suggest is just trying a point on each side of the x and y intercept. So x equals -1. Just plug that into our function. And you can plug it in either in the factored form or the original function. But either way, we're going to get a positive answer, right? We get 1/3. And the whole point of that is that it's going to be positive, so it will be above the x-axis, somewhere in there. And so the graph will continue toward that x equals -2 vertical asymptote. So now plug in something on the other side of the origin. So x equals 1. If we do that, we get 1/3. But our denominator is negative. So we get -1/3. And the important part here is that it's negative, so it will be below the x-axis. And both sides are going to hug the vertical asymptote. So let me just draw that a little better here. So the middle of our graph is going to look like this. So notice it crosses the line y equals 0, which is an example of a graph where it's violating that horizontal asymptote. And that's okay. Remember that the horizontal asymptote is most helpful in telling us the end behavior of the graph. So where x gets really, really small and really, really big. So now let's figure out what happens with our graph when we are to the left of the vertical asymptote and to the right of the vertical asymptote. So let's pick another point to try. So let's plug in x equals, say, -4. You can pick anything you want, but -4 seems like a good number. So just plug that in here, and let's see, what do we get? So we get -4. This becomes -2. This becomes -6. So that's going to be positive. So we get -1/3. Just so happens to be 1/3 again, right? But the important part of doing this is it's telling me where it's going to be on this graph. So I know it's going to be in this little quadrant of the graph. And likewise, when I plug in x equals 4, I get 4/6 times 2, which is going to be positive 1/3. And again, I'm just trying to kind of eyeball what section of the graph this will be in. Because in these far sections, the graph is not likely to cross the horizontal asymptote, and it definitely will not cross the vertical asymptote. So usually we are just required to show the intercepts and maybe one point in each section of the graph. So looks really complicated, but it's really not that bad. So you're welcome to plot more points if you want, but basically this just gives us a really good idea in order to sketch the graph for this function. So remember, you just want to make sure that your graph never crosses those vertical asymptotes. And again, near the origin, the graph does cross the horizontal asymptote in this case. Okay, last problem, and this one's a little different. If you're feeling good about it, definitely pause the video, see how you do. So let's factor first. And again, we're going to factor on the top. And then, we're going to have a common factor here in the numerator and the denominator. So this is a situation where we will find a hole in the graph because we have common factors that cross out and simplify, and we're left with a function that is simply x plus 1. And x plus 1 is just a line. So where we had that factor that crossed out, x minus 2, set that to 0, we get x equals 2. And that tells me that the whole will occur where x equals 2. So plug in 2 into my simplified function. 2 plus 1 equals 3. So I get a whole in the function at the point 2, 3. And I will show that when I do the graph, I'll show that as an open circle on the graph. Okay, the rest of this is pretty straightforward because my function just simplified to a line. And it's simply a line with a hole in it. It's not even a rational function anymore. So we won't have any vertical asymptotes or horizontal asymptotes. We do have an x-intercept at -1, 0, and a y-intercept at 0, 1. No vertical asymptote, no horizontal asymptote, no slant asymptote. So what's the domain? Well, recall the domain is every value of x where the function is defined. So the function is not defined when x equals 2 because that's the x value of that whole. So my domain would just be -infinity to 2, union 2 to positive infinity. And on a problem like this, you might also be asked, what's the range? Well, the range, remember you read from the graph from the bottom to the top. So you would say from -infinity to 3, the y value of the whole, union 3 to infinity. So then when we graph this, that's pretty easy. It's just the graph of a line, y equals x plus 1. So start with my y-intercept of 1. And we have a slope of 1. See if we just go through all the little corners of the boxes here on the graph. And that's my line x plus 1. But wait, I have to show that there's a hole in that line at 2, 3. And that's where that line is not defined. So we're going to draw the hole as an open circle. And then the rest of the line is just the equation of that line. And that's it. So that looks like a complicated one, but really that ends up being one of the most easy functions to graph. So remember, if there is a hole in the function, you do not use that x value of the hole as a vertical asymptote. That's a common mistake that students make. So I hope that these 3 problems have helped you review rational functions. Thanks so much for watching and have a great day.